Right, and then I'll stay on the text channel for this class. Alright, so the YouTube stream is up. I'm gonna close that window. No, today's topic is not gonna show up in the exam. So the exam is the scope of the exam, as my mind map here indicates from last time, is all the way up to and including binary comparison. So all the flags, signed versus unsigned, base conversion, binary addition, binary subtraction, all the gates, right? The NAND gate, the AND gate, the OR gate, the NOT gate, carry look ahead, borrow look ahead, carry repo, and so on and so forth. So those are all included in the scope of the exam. So don't let the practice test limit what you think the exam may contain. So there we go. Alright. I will answer DMs later on because we are really close to the start time of the lecture. So I think we are ready to go. I'm just waiting for the official time to start in 40 seconds. Gotta start on time. Yeah, no mind map today because this is kind of like a brand new topic. So there's really not a whole lot that we have to remind ourselves of. So that's why no mind map for today. Alrighty. We got 1 second to go. There we go. Alright, so official start time. If I need to summarize double precision floating point numbers, this is it. Okay, this section 2 right here that you're seeing on the screen. Yes, my face is covering a part of it, but you can open the same document on your side, in your own browser. So this basically sums up what is a double precision floating point number, and there's really not much to say. I'm just kidding, because well, the most interesting part about a double precision floating point number to me is not about how the bits are utilized, because this really does summarize how the bits are utilized. The interesting part is how do we do a conversion. If I give you a base 10 scientific notation number, how do we convert it into the double precision floating point number that basically IEEE specifies? That is of interest to me, the conversion part, not so much how the bits are utilized. So what I'll do is I'm going to start reading this part here, and you're more than welcome to right click on this link so that you can go to a Wikipedia page. Why don't I do that? So this is the Wikipedia page on double precision floating point number format, and the most important part of their representation is the picture. That's the one part that I don't really want to reproduce, is the picture of how the bits are utilized. And so they have basically an equivalent explanation of how the bits are utilized compared to the explanation that I have. They're basically exactly the same thing. It's just that the indexing is a little bit different. I choose to use -52 to -1 because that truly reflects what those bits are corresponding to in the Mantissa. Whereas the Wikipedia page chooses to use 1 to 52. It's because they want to actually look at the bit position in the double precision format as a 64-bit number, and I want to look at it from the perspective of the position of those things in the Mantissa. Alright, so before we start to talk about this, let's think about how we represent certain values, okay? And because from that discussion, this stuff here will suddenly start to make lots of sense. So we'll go ahead and start with an example, and I'm going to use Notepad for these examples, just because most of what I need to represent do not need to be, I don't need special mathematical symbols for the most part. So there we go. So here is my what is equivalent to Notepad in my Linux installation. And this is one of the very few parts where Logisim is not really useful, it's not needed. So there's a lab today before anyone asks, because I know some people really like to ask, do we have a lab today? Yes, we do have a lab today, but it doesn't involve the use of Logisim. Alright, so getting back to the representation thing. So let's just say that I want to represent, I'm just going to pick a number. So let's pick 80. Okay, so 80 is a base 10 number, and I want to find out how to represent it in base 2. And most of you should know how to do the conversion at this point. So, the easiest way, the most intuitive way to do this is to figure out what powers of 2 do we need in order to sum up, to the amount of 80. So that doesn't take too much work, right? Because, we have 64 in base 10 plus 16 in base 10. Okay, that's not very difficult. So then we can now convert 64 to a binary number. 64 being 2 to the power of 6 in base 2 is going to be represented as 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. Okay, so now it's a base 2 number. And then 16 is 2 to the power of 4, which means in base 2 it is 1 followed by 4 zeros. And now this is a base 2 number. Once I add these two numbers using binary addition, then I end up with 101, 0, 0, 0, 0 in base 2. So that's the usual base conversion thing. I mean, you can do the base conversion using the formula that is in the base conversion module. That works too. It's just in this case, I don't really need that. Okay, that equation is really useful for kind of bases that are odd. Something like 5, 7, or something like that. For base 2, usually it is fairly simple because it doesn't even need division. It just needs comparison in this case. So now you look at this and go like, what if I want this to be represented using a quote-unquote scientific notation? So when we refer to scientific notation, we basically mean that there's a mantissa, okay, and followed by, so the mantissa is multiplied by some base to the power of some exponent. Okay, that is how we represent a value in quote-unquote scientific notation. So a few words about the mantissa. So mantissa is supposed to be normalized, and I think we have already explored this. So it has to be greater than or equal to 1. So mantissa has to be a quantity that is greater than or equal to 1, but at the same time it has to less than base. So in base 10, the mantissa cannot be 10 or more. It has to be less than 10. So that's the normalization, okay, which basically means we want the mantissa to be between 1 and up to but excluding the base. And then the rest is up to the base to handle. So the base to the power of exponent is an integer. It can go positive, it can go negative, it can also be 0 if that is what works for this particular value. So, and then base is typically, okay, in base 10, we are using 10. In base 2, we're using 2. Other bases, not so useful, so we are mostly just concerned about the base being 10 or 2. I'm going to pause here and see if there are any questions up to this point. Because some people might be relating this material to the lab that we did, I think, last Thursday, which is good. Okay, if people draw a relationship between this stuff and last Thursday, that's good. Excellent. We got a few people typing. V is just a value. Whatever value we want to represent, we want to use this format to represent a value. What do we call it? How about just value? V for value. Does that work? All right. Alright, so it looks like we don't have any further questions. So now we're going to look at this number here and go like, how do we do this in scientific notation? Of course, the first question is, what scientific notation? Which base are we talking about? So let's deal with the easy one first, okay, in base 10. So the base 10 scientific, I'm going to just use SCI for scientific notation of 80, which is already in base 10. That's pretty easy, right? The Mantissa, since it has to be between 1 and 9.99999, 8 will work. And then we just say this is 8 times 10 to the power of 1. Okay, so that's the scientific notation, and typically using the notation that we have already talked about, this is denoted as 8E1. So this E here is once again not the natural log constant. Yes, this is not natural log constant. It is simply a separator to separate the mantissa from the exponent. That's the purpose of this lowercase e here. Okay, so that's pretty easy. What about in base 2 then? Okay, what about the base 2 scientific notation of 1010000 in base 2? What is that? So what we're going to do is we're going to say, there's always an implicit point right here, right? Because this digit is representing the number of 2 to the power of 0, and the purpose of the decimal point, in this case the binary point, is to separate the digit representing the quantity of 2 to the power of 0 from the digit that specifies 2 to the power of -1. That really is, it serves the same purpose in a base 10 number. It's just that one is in base 2 and the other one is in base 10. So now we look at this and we add some additional components, okay? Because I can always say that this is the same thing as this number times 2 to the power of 0. Because 2 to the power of 0 is just 1, okay? It doesn't really change anything. So now I'm going to look at this and go like, I want to somehow shift this binary point all the way up to here, up to between the leftmost one and the 0 that is to the right hand side of the leftmost one. So I'm going to do this step by step, and then we'll figure out how this works. So now we have 101,000.0. Yes, I know we have trailing zeros, but just humor me and tell me, how do I establish this equality? In other words, I have just made the mantissa 1/2 of the value that it used to have. So what do I need to do? Exactly, so Lisa is correct that I have to adjust the exponent so that now it is 2 to the power of 1. And you can probably see what I'm going to do next, okay? And this is 2 to the power of 2 because now I have divided the original quantity here by 4, so we have to multiply the whole thing by 4 in order to establish the equality over here. And if you guys want to, we can just kind of copy and paste this several times until we are done with the whole thing. Alright, so with each step, okay, I know some of you are thinking, oh, this is absolutely boring, which it is. Okay, so now we have 2 to the power of 3, and this is to the power of 4. We have to move this one all the way over here. Yes, so Richard is correct about that. And we need just one more row, but I do want to finish this just so that people who are more visual in terms of learning style is going to look at this and go like, oh, I can see how the dot is going in this direction, and I can also see how the power of 2 is increasing accordingly. I personally probably am not a visual learner. I have no idea what kind of a learner I am. I have been told that I'm a random learner. I learn things, in random pieces, and somehow my brain would find the relationship between all the things and just form a mash, kind of messy mash in my head. All right. So Jonathan's wrote, it's kind of weird since 2 and 6 are greater than or equal to 2, the base. I'm not really sure what the 6 is referring to? Oh, you mean this 6 over here? Okay. That's okay. I mean, that's just the exponent, right? That is really just the exponent. And this part is in base 10. Okay, so this part is in base 10. There's no restriction, where I have to represent the entire expression using one single base. I can mix and match, because after all, a number is really just a way to represent a value. So as long as I can still represent the same value, I can choose to use whatever base I want for each number. And the implicit thing is, if I don't specify the base, it is in base 10. So, oh, wait, Tech. I think we just got it, right? Because now we have gotten the Mantissa in base 2, in this case, is 1.010000, and we also have figured out that in base 2, the exponent is 6. Are we good up to this point? Excellent. All right, good, very good. So now the question is, so now that we have a way, okay, it seems like we have a method to convert any value into the format where we have a base 2 Mantissa and a base 2 exponent. And now the question is, how do we put all of these bits into a 64-bit number so that we end up representing 80 in this case, 80 in well, when I say 80, it's a quantity. 80 is a number in base 10. So how do we do this? And Daniel said, why did we add parentheses 10 to the base and the exponent? Because Jonathan was asking, why do we have 2 and 6 when we're dealing with base 2? And the reason is because 2 and 6 are still in base 10, and putting parentheses 10 after a number simply re-emphasized, totally overkill, that this is in base 10. That's why. Okay, now oh, you're welcome. So now we look at this number and go like, it looks like we got a bunch of a whole lot of pieces that we need to somehow fit into a 64-bit chunk of bits. Okay, so what is also implicit is that there's a sign, right? Because a double can represent positive and negative values. So in this case, the sign is a 0, meaning that the value is non-negative or positive. So we have the sign, we have the Mantissa, and then we have the exponent. Okay, so now we need one more extra concept to get this done. Okay, so this exponent here, which is 6. Okay, so I'll put it here. So exp2, which is the actual exponent of 2, is 6, which is 110 in base 2. Okay, so you would think that somewhere we're going to have 110 in that 64-bit representation. That is not the case, because when we actually represent the exponent, it's going to be biased. Okay, so the biased, okay, and I will biased. There we go. So the biased exponent of base 2 is actually whatever is the actual exponent in base 2 plus 1023. So in this specific case, the biased exponent is going to be 6 plus 1026, 1023. Sorry, I wrote the right number and then I said the wrong number. So this is 1029. Which is 1024 plus 4 plus 1. So the representation of the biased exponent is actually going to be a little bit strange, because 1024 is 2 to the power of 10, which means we're going to end up with 10 zeros after this one. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 1 is this one over here, and then the 4 is right over here. So this becomes the actual bit pattern to be represented in a double, okay, because it is biased. Now, if you want to ask how come the IEEE decided to use the biased method instead of using a signed integer that is 11 bits wide, I cannot answer that question because I was not part of the IEEE, and I'm still not part of the IEEE to determine standards. Okay, so you have to ask the people who came up with the standard and ask, why did you use a biased representation instead of a signed integer representation? My guess is they were not computer science people. As much as electrical engineers try to think that they are computer science people, they are not. And I know of one particular professor in one of the sister campuses who was an electrical engineer, and he kind of switched into computer science and teach programming classes. I probably should mention this to him one of these days. All right. Okay, so moving on. So we got a bunch of bits now, right? So we got the sign bit, which is a 0. We got the biased exponent in base 2, and that turns out to be 1. And okay, I am too lazy to count zeros, so I'm just going to copy and paste. Alrighty. And now we had, and then you guys would go like, well, we know what the Mantissa is. Yes, we do. But the interesting thing is not the entire Mantissa is going to be represented. And you might ask, why? Well, that's because as far as a base 2 Mantissa is concerned, because in base 2, a Mantissa has to be between the value of 1, it has to be greater than or equal to 1, but it also has to be less than what we know as 2, okay? Which in binary is going to be 1.1111111 all the way to the right hand side. So that means this digit here is guaranteed to be a 1. There's no way this can be a 2 because the digit 2 does not exist in binary. And there's no way this can be a 0 because if it were a 0, then the Mantissa is going to be less than 1, which is not what we want. So the digit that I have highlighted here is guaranteed to be a 1. So if you already know a particular bit is guaranteed to be a 1, why do you want to waste one bit to represent it in a representation? The answer is no. You don't want to waste your storage even one bit. So in the actual representation, we only store the fractional part of the Mantissa. So now we specify here and say this is the fractional part of Mantissa is going to be 0, 1, bunch of zeros after that, and a whole bunch of zeros. Okay? How many zeros, you might ask? Well, let's figure this out, right? This is only taking one bit, okay? One bit is enough to tell us whether the entire double representation is negative or non-negative. In this case, it is non-negative. This is taking up 11 bits, and that's what the standard specifies, okay? So why not 12 bits? Why not 13 bits? That's the standard, okay? And I wasn't part of the body to determine the standard, so for now we just say, yeah, we know, just 11 bits over here. So now we have used up 12 bits out of 64, so that means the Mantissa has 52 bits, okay? So there are 52 bits here to represent the fractional part of the Mantissa, and for the value that we are representing here, the rest are all zeros, okay? So I'll just go ahead and kind of give you a really rough representation here that there are 52 bits over here. There we go. ASCII art. Take that. And of course, for those of you who go like, but my drafting teacher in design technology said, this is not proper. Fine, we'll use an arrow. There we go. This will make Randy Schuster very happy because this is actually, the kind of notation people like in CAD drawing. So there we go. Alright, so now we have used up all 64 bits. The next question is, in what order are these bits arranged? In a double precision floating point number, which is basically just a chunk of 64 bits. As it turns out, that part is really easy. The sign is the most significant bit all the way to the left hand side, and so I'm going to use a bracket notation here just so that we can say this is the sign, and then now we have the biased exponent of base 2, and now we have the fractional part of the Mantissa. There we go. And so when you string all the bits up in this particular format, you have a 64-bit chunk that is otherwise known as the IEEE double precision floating point number. Alright, so Daniel is asking, where did the 1023 come from in the biased exponent 2? That's just part of the standard. Okay, when we represent it, we add 1023 to the actual exponent of 2 and then represent the biased version of the exponent of base 2. So the technical answer to Daniel's question is the IEEE standard body decided that this is how we want to represent a double precision floating point number. There's no other explanation in this case. Is that okay? Is that good? Alright, I'm not seeing any questions. And I kind of resist to click this button. I don't think you guys can hear it if you're from the when you're listening through the Discord channel, because the Discord channel only can get my mic, and what I played was going through the desktop audio. So the YouTube people can hear that, but not so much the Discord people. Yes, it is always 1023 plus whatever the actual exponent is. That is correct. So Lisa is correct on both counts. All right. Yeah. Okay. So now the question is, well, Tack, you've mentioned all of this stuff here. How do we know that you are speaking of the truth? How can we check something like this? So the next part of the lecture is really to show you, how we can double check and verify all this stuff here. There are several ways to do this, and I'm going to show you one way which is kind of obscure. It will basically test your knowledge of C and C++, mostly just your plain C. C is a subset of C++ for the most part. So I'm going to introduce you to online GDB. Okay, so let me type the URL because you cannot see the URL the way I place the windows. So I'm using onlinegdb.com. So if you guys are interested, you can also go there if you want to. As far as I know, okay, that's all I can say. It is not a bad website. It doesn't seem to infect my computer. Then again, I'm using Linux, so when it comes to getting infected, it's not harder, so to speak. It's just that most people don't want to waste their time to target like 1% of all the computers. That's part of the reason why Linux is slightly more secure. And then Lal, ask, and how was 1029 changed to 1024 plus 4 plus 1? Because 1024 plus 4 plus 1 is 1029? I know I'm answering the question in a circular fashion because that is how I do base conversion. When you do base conversion, what do? You express the value in as a sum of powers of 2. That is why. This is going all the way back to base conversion. Exactly. So I'm changing it to binary, which means I need to re-express the value as a sum of powers of 2. Alright, so it's time to take row. Alright, so let me switch to the row taking screen and share that with you right here. And I'll show you the word and copy and paste it into the text channel. So there we go. So the row taking word is float. There we go. I'm pasting it into the text channel so you can just copy and paste it into the activity. There's not much else to do. Save and publish. And you have until 9:36 to do it. It is still 9:27 right now, so you have about 8 minutes to do it. It will take you about 8 seconds to actually do it. All right. I should probably have badges, to reward people being the first, second, and third to get to the row activity. Well, in this class, there's a saying of whatever floats your boat. We don't care about boats, okay? We do care about doubles. So whatever float your doubles. Time to float. Well, I bet you most teachers don't even bother to make their online classes synchronous. I know of certain people who absolutely do not want to do synchronous classes because a lot of professors teaching online would rather just go to Canvas, push a button, reset all the tests, reset all the dates, and then they can walk away for the whole semester and not to have to bother to do anything else. That to me is just boring. Yeah, I cannot do that. So as much as some people want to request that I do the same thing because Professor blah 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 is doing that, how come I'm not doing that? So my answer is quite simple. How other professors teach their classes is none of my business. That's all I can say. Alright, so I'm going to explain this program in just a little bit, okay? Which doesn't seem to have anything, absolutely nothing to do with floating point number representation because there's no double in here whatsoever. So it's like, why are we doing this program? So I'll answer that question in just a little bit. Alright. Oh, I'm pretty sure I'm hurting my reputation too, quote unquote reputation, when I went online because I don't really I'll put it this way: I don't meet the expectation of certain people that online classes should be asynchronous and they should be easier. So not here, not in my classes. Anyway, so I'm going to look at this program and go like, this program seems pretty useless, right? All I do is to define a variable which is a uint64 underscore t, and I included an extra header file called stdint.h. That is standard integer.h, which defines a few types, this being one of the types, and this way I know for sure that x is an unsigned 64-bit integer. Because if I just say unsigned, who knows? I mean, how can you tell whether the unsigned is 16-bit wide, 32-bit wide, or 64-bit wide? You cannot, okay? Because it depends on the platform where the compiler is running. So if you compile it in the 16-4-bit platform or an 8-bit platform, then unsigned by itself is going to be 16-bit wide. If you're using one of the older computers and it's a 32-bit operating system, then unsigned is going to be 32-bit wide. But if you're using a newer computer and it's a 64-bit operating system, then unsigned is 64-bit wide. So if I just use the word unsigned or the word int, I have no control over how wide or how many bits are actually allocated to the integer. So that is why this header file is super useful, because by including standard integer.h, I can now refer to these types specifying exactly how wide I want the integer to be. Now, you cannot have 24-bit wide, you cannot have like 34-bit wide, so they go from 8, 16, 32, and 64. So those are the options that you can specify. But this is really rather useful, okay? So I hope you guys will remember this in your other classes, because there are certain types of programs where you really need to control, or you need to specify the width of integers, because you already know the range of values that those integers need to represent. So in those situations, it is always best to utilize standard integer.h so that you can specify the exact width of those integers. Okay, so I got some questions here. On a computer that only supports 32-bit, it will still adjust, it will still be 64-bit wide. X will continue to be 64-bit wide. Internal to the compiler, it will basically crank out the code to perform 64-bit addition, 64-bit subtraction, and whatnot using only 32-bit instructions. But that's up to the compiler. The compiler will handle that. Well, 32-bit computers can handle floats, and even older computers, even 8-bit computers can do it. Okay, I will show you this one thing. I know it is digressing a little bit, but it's not too much. So if you look into Arduino, okay, Arduino. Okay, there we go. I haven't used Arduino for a long time, so it becomes kind of difficult for me to type it because my muscle memory is gone typing Arduino. So if you look up Arduino, okay, and go to the web page, it's a tiny little single board embedded computer. Okay, that's kind of the technical term of what it is. And it's an 8-bit processor. Okay, it's a tiny little wimpy 8-bit processor running at, if I remember correctly, 12 megahertz or something like that. So, but it can still handle double. You can still, declare types in double, like as in double precision floating point numbers. You can continue to use 64-bit integers and so on. So the compiler handles all of that stuff here. The difference is, on an Arduino, we are using a tiny little 8-bit processor that can only work with integers to do all the double math, which means it's going to be really, really slow. Yeah. So that's why you want to avoid using double when you don't have processing resources. It is not a matter of whether we can do it, it is a matter of how quickly can we do it. All right. So I hope that answers the question from Colton. And by the way, Arduinos are really fun. You can hook it up to a circuit board or breadboard. Hook up LEDs, motors, and all kinds of other stuff. If you look up on the internet, there are tons of projects that people have done using the Arduino board. If you want to upgrade, you can upgrade to a Raspberry Pi, which runs Linux, and you can do a lot of stuff with a Raspberry Pi. So really kind of cool stuff, but a little out of the scope of what we are talking about here. Alright, so getting back to this program. So now I can specify that this program is written in C. It's not C++, this is just plain old C. Okay? And in fact, I think this program will compile using some of the really, really old C compilers, because I'm not using any of the newer features of the current C compilers. Next thing I do is I click on debug. The program does compile, should compile, and now I'm in the debugger. Okay, so this is the part where most of you, or some of you, many of you, will cringe. You go like, are we going to use command line stuff again? Are we just going to type something to control the behavior of the debugger? The answer is obviously. When you see the blinky cursor, what else are we going to play? What else are we going to do when you see the blinky cursor on the black screen and some text on it, right? Fixed size font, those are all giving away that, yeah, we are going to type the commands. We are not going to do the GUI stuff. All right, so now we put a breakpoint. B is for break, so we are going to put a breakpoint on line 17. And then R for run, okay? So we're going to run the program all the way up to line 17. So line 17 has not executed yet, so we are right at the cusp of returning from main. And you guys will say, but this has absolutely nothing to do with double precision floating point numbers. You're correct. Up to this point, there's nothing to do with it. So what we are going to do next, what I'm going to do next, is to make sure that my auto tab closer thingy does not close this tab. So I'm going to have to tag it to say, don't auto close it, or don't suspend it. And there's a way to do it. I just have to remember how to do it. Okay, auto tab discard, and I have to specify. You cannot see this because it's off the screen. I'm going to have to tag it so it won't. Always keep this tab for this site. Keep this tab for this session. I'm going to say keep this tab for this site. So this way, my little auto tab closer thing, to help me save resources, is not going to close this tab automatically, because that would not be good. By the way, for those of you who want to say, but I want to save this file, I want to refer to this file or whatever program I have written here from time to time, that's perfectly okay. You can go to, you can actually save it. Let me see, is the save button here? Yep, there we go. And you can even use Control S. So I have to sign in first, and I can use one of these three things to sign in. So the point is, if you sign in, okay, then you can actually save the file on their side for free. So this side doesn't even ask you for money. Now, if you get suspicious and go like, well, but I don't want them to use my personal, Google account or whatever, sign up for a next, free Google account, right? I mean, and then use that for online GDB and only for online GDB if you worry, okay? So there's no reason why not to use online GDB. All right. Yes, I did say quite clearly that this is plain C. This is not even C++. There's nothing in here that has to do with C++. Yeah, this is very nice because you can use it on the tablet, you can use it on a Chromebook, you don't have to install your own compiler, everything is already on their side, okay? All you have to do is to just be able to type. So assuming your tablet has a reasonable keyboard, physical or otherwise, it's gonna work. I'm not sure whether Replit is going to work or not. It depends on whether it has a debugger. If Replit has GDB, then yes, what I'm going to do here, you can also do it over there. But on the other hand, if it doesn't have GDB, or at least the exposure of the command line portion of GDB, then what I'm going to do here is not going to work on Replit. I haven't used Replit for a long time, so I'm not really sure whether they have now a GDB for C and C++. But when I was using it, they did not have GDB. So I think Replit is best for JavaScript, Python, that sort of stuff. With C and C++, I don't know whether they have the debugging tools or not. All right, so now we're gonna switch back to the text screen here, because now I need to say, okay, how do I put this number into the whole thing? Okay, so first of all, we're going to look at this number as a binary number. So it's going to be pretty easy, concatenation of all the bits, right? So I'm going to do it in a lazy fashion, because all I'm doing here is really just copy and pasting. Okay, so and here's copy, paste, and then copy and paste like so. And obviously we're going to have a whole bunch of zeros. So right now, we don't have 64 bits just yet. So I'm just going to use this notation to say that, fill it up with zeros until we have 64 bits. All right. So one thing you might notice is C can automatically accept numbers in base 10. That kind of goes without saying. You can specify in base 16, which is hexadecimal, which is something that we are going to talk about right next to this. It also has base 8, which is octal, but it doesn't have base 2. Of all the bases that are useful, base 2 is not part of the standard of C. Now, don't ask me why. Once again, I'm not part of the body that decided the standards for C and C++, but you cannot input a binary number in C and C++ and expect the compiler to be able to deal with it. So what are we going to do? Well, so this is where I'm going to introduce hexadecimal numbers. So hexadecimal numbers are pretty easy. So you basically go from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on, like that. And the last one is going to be 1, 1, 1, 1. So now this is in binary. So let me just put a column name here. This is binary, and this one is hexadecimal. Now hexadecimal is not base 6 because hexa is 6, deci is 10. So combined, it is base 16. So the base 16 representation of 0 is just 0, one single digit. And this is 1, this is 2, this is 3. So There we go. And by the time we get to some of the more common digits that we are familiar with, 1001, which is 9. And now we have a problem because 1010 is what we know as 10. And when we write the quantity of 10 as a base 10 number, it takes 2 digits, right? Because it is 10. But in hexadecimal, it is a single digit. So we don't have a normal numerical digit to represent the quantity of 10 because when we work with base 10, 10 as a quantity is specified as 10 because 10 is the base. So what we do here is we're just borrowing our letters from the English alphabet. So A, which can be lowercase or uppercase, is representing 1010 in base 2, which is what we know as 10. 1011, which is 11, what we know as 11 is B. 1100 is C. 1101 is D. 1110 is E, and then finally 1111 is F. So that is the table, not complete, because I'm missing kind of the stuff in between. But this is the table to convert from base 2 to base 16. Now the most important part here is we chunk. Okay, we have to basically group the bits into groups of 4. We convert a group of 4 bits at the same time to a base 16 representation. And if you ask why, the answer is quite simple. It's because 16 is 2 to the power of 4. So every 4 bits, every 4 binary digits corresponds to one single hexadecimal digit. That makes the conversion really easy. Because if you want to convert, into base 6 or convert into base 9 or something like that, you need a whole lot of division, okay? But to convert from base 2 to base 16, it's just table lookup. There's no division whatsoever. Okay, so given this is the approach of how we're going to do it, now we break it up into chunks of 4. Okay, so chunks of 4, chunk of 4, chunk of 4, chunk of 4, chunk of 4, and so on. So now we look at this, we look up the table. Okay, the first one is a 4, this is a 0, this is a 5, this is a 4 again, this is a 0, and we just have a bunch of zeros all the way to the end. Okay, so let me read the text channel and see if there are any questions. Okay, very good. So now the question is, how many zeros do we need here? Because tag, you were not being very specific here. Well, think about it. We need 64 binary digits, and there are 4 binary digits to one hexadecimal digit. So the question is, how many hexadecimal digits do we need? Signed integers in there are no such thing as a signed integer in hex. Hex is really just representing the zeros and ones. How you want to interpret the zeros and ones, in other words, whether it's a signed interpretation or otherwise, it's not encoded into base 16. So when we use base 16, we're just working with a chunk of bits. And Jonathan is correct. That is the correct answer to the question that I asked earlier. So there are 16 hexadecimal digits. So we'll just go ahead and say that we have 6 here. So we just need 10 more, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And now we remove all the spaces, okay? Because I'm just preparing to copy and paste onto the other side. And there we go. And in C, if you want to specify a hexadecimal number, you have to prefix the whole thing with 0x. Lowercase or uppercase, I think is okay. If you use uppercase X, then all the A to F, they also need to be uppercase, if I remember correctly. But I know if you specify everything in lowercase, it definitely works. Okay, so I just copied this block of hexadecimal digits, and now I'm it's not being debugged. Okay, it did time out, even though I told this time it's not a browser thing, this time it's on the other side, because when GDB is running, it's probably taking up memory space, and whoever is running this website decides we don't want people to be wasting memory space, that's okay, not a problem. So the breakpoint is still there. We're now getting back to where it was earlier. So in the debugger, one of the great things you can do with any debugger is you can change the value of variables that are in scope. So in this case, we can change the value of x, and the command to do that is set var x equals 2, and then you can specify the new value of x, which in this case is the chunk of hexadecimal digits that we just copied. So I'm going to paste it here. Paste it here. Nope. No, it doesn't like to get pasted. Oh, what am I going to do? Paste. There we go. Okay. So I just pasted it here, press the enter key. Now we're going to say, oh, so does that mean that if we print x, we're going to see 80? No, not even close. Oh, maybe we should print it in hexadecimal. So print /x is forcing the output to be in hexadecimal, and we get the original thing back. Okay, not surprisingly, right? So the question is why? Well, that's because this is an unsigned. We are looking at the same 64 bits, but the interpretation of the 64 bits is simply as an unsigned 64-bit integer. So that means bit 63, which is the most significant bit, is telling us the number of 2 to the power of 63, and so on. That's not, this is the wrong interpretation of all those zeros and ones. So now the question is, how do we force GDB to interpret those bits correctly? And someone's going to say, we can typecast it. Okay, so typecasting is actually an operator, in C. So we can say double, which is basically forcing the translation into a double representation of x, and it gives us something like this. It go like, no, that doesn't look like 80 to me. Why? Well, that's because this is actually re-representing the value of x as a double. Let me say that one more time. It is re-representing the value of x as a double. So the question is, what is the value of x? The value of x is based on its actual type. So in the program, x has a type as a 64-bit integer. So the way we get to the value of x is still looking at the 64-bit as if it is a 64-bit unsigned integer, and then we take that value and say, oh, okay, now we want to represent that value as a double, which defeats the whole purpose, right? Because what we really want to do is to say, no, don't look at these 64 bits as a 64-bit unsigned integer. Okay, to be more specific, bit 63 is a signed bit, bit 52 to bit 60. No, yes. Bit 62 to bit 52 is the biased exponent of 2, and then bit 51 all the way down to bit 0 is the fractional part of the Mantissa. That's how I want you to look at it. Typecasting is not going to fix the problem, at least not this kind of typecasting. Alright, so Richard is typing in the text channel. I'll keep an eye on the text channel, but other than that, I'm going to do something that you should know already because of CISP310. And Richard typed, so we basically mapped the value of 80 to another representation. That is correct. Okay, and this time it is a basically it's a scientific notation, but in base 2. That's basically what a double really is it is a scientific notation, but in base 2. Alright, so getting back to our problem here. Okay, so I'm going to ask a few questions. So don't copy this, because as far as I know, this is all getting recorded. It's getting streamed to YouTube, so there's no point in copying this. But you might want to use this opportunity to ask questions if you're not clear about what I'm doing here. Alright, so first thing is, what is this? Ampersand x. What is that representing? Exactly. So it's basically looking for the address of x. So now let me ask you, what is the type of ampersand x? You can type in the text channel. because that is a little bit, it's an int pointer, exactly. So it is a uint64 underscore t asterisk in this case. It is a pointer, or it's an address. In this case, pointer and address is interchangeable, so it's a pointer or address to a unsigned 64-bit integer. Okay, very good. So the next question is, can I typecast an address? We know that we can typecast just an integer, but the question is, can I typecast an address from the address of one type to the address of another type? In other words, can I do a typecast here? So I'm not typecasting the value of x, I'm typecasting the address of x. Do you think there might be problems? Exactly. So there's no reason why we cannot. Alright, so I'm going to do some typecast here, and the way I'm casting it is I'm casting it as a double, the address of a double. So I am taking the address of a 64-bit unsigned integer into the address of a double. That's perfectly okay. This is why C is both a very efficient language and also at the same time a very dangerous programming language, because it let you do stuff like this. As far as I know, there are no other programming languages that will let you do stuff like this. But this is the kind of stuff that you need if you want to write an operating system. So, and obviously people who have only learned Java may have some questions at this point. I'm hoping this class does not have people that only have exposure to Java but not in C or C++, because those people will have some catching up to do. And I'm not going to be responsible for that catching up. Alright. Okay. So now I go like, so if I press enter key, the enter key right now, it's just going to show me the address of x. But it's going to say, but this is not just the address of anything, this is the address of a double now. So the next thing I'm going to do is to say, let's dereference this particular address. So this is where the fun begins, because instead of looking at 7FFFF, a whole bunch of stuff, EB, E8, which is what we see, in the previous line here. So instead of looking at that particular address or the 8 bytes at that particular address and say, this is, these 8 bytes, form a 64-bit unsigned integer. Now the compiler, or the debugger to be more exact, is now looking at those same 8 bytes, the same 64 bits, but it's going to say, but these 64 bits is a double. It's not a unsigned 64-bit integer anymore. So when we dereference it, it is going to interpret those 64 bits as a double this time. Okay, so when we press the enter key, we get 80. So this exercise right here, serves several purposes. One is kind of to get you reacquainted with stuff that you learned from C, from your CISP310 class. And trust me, the whole concept of pointers and pointer arithmetics and stuff like that is going to come back in, I would say, about week 8 of this semester, and it's going to come back hard. Okay, so that means this is just a little warm up, so that when we get to that point, we're going to go like, yeah, we get pointers. We totally get what a pointer is. So this is a very nifty little trick, okay, and it goes the other way around too. Okay, so I can later on show you how it goes the other way around. But let me just pause and shut up and see if there are any questions at this point. Excellent, we got a few people typing. Alright, so the first question is the part where you use double asterisk getting the value of the address of x? So double asterisk is okay. It just timed out again. So the double asterisk is the typecast operator. It's basically telling the debugger how to look at the expression to the right hand side of the typecast operator. So it's just telling the debugger, don't look at it as a address of a 64-bit integer. You look at it instead as an address of a double. That's all it says. I'm confused why you did 1e asterisk. 1e asterisk. Not sure what that means. So Jonathan, if you can clarify in the debug input. Unfortunately, we just lost it. Ampersand x1e. No, that doesn't look right. All right, so let's do this one more time. And this time we'll do it in a super high speed. Super high speed replay. Here we comes. Let me see if it remembers. Oh, it does not. Okay, sometimes it remembers commands from the previous run, but not in this case. That's okay. We can very quickly do this. Oh, why is it complaining? A syntax error in the expression. Okay, so there we go. We have set the variable to that, and now we have. So let me just repeat the exact command that we had before. This is ampersand x. This is the expression that printed 80. Oh, good, very good. So Colton has a screenshot. Unfortunately, when I look at the screenshot on my Discord screen, it doesn't show very well. So I'm gonna have to open it in the browser. And that doesn't seem very. There we go. Oh, you mean this thing here? That is. Huh. I don't remember putting it there. I think that's a leftover from somewhere. I think it is a leftover when we printed the address. So it's basically the terminal. It's a problem with the terminal emulator. The terminal emulator might be picking up some garbage from before, but the actual expression is not that. The actual expression is what you're seeing right here. That is supposed to be what it should be printing. Yeah, okay. Well, very good. I mean, you guys are spotting, the bug. I didn't spot it because I already knew what it's supposed to print. But you guys were looking at exactly the expression and go like, where's that garbage? So it is really left over from the terminal emulator. All right. Very good. Okay, I'm glad you guys are paying attention to the details. But this is what it's supposed to look like. It is just a dereference of the typecasted address of x. There we go. Alrighty, let me take a look at the time. We got about 18 minutes left. Okay, so let's reverse the process. Okay, so reverse the process means, I have a particular value and I want to use this technique to get back into the bit representation of the whole thing, and then we'll see whether that makes sense or not. Okay. So that's what we're going to do next. Alright, so I can't really do that now in the lecture. So maybe during the lab time we can take a look at that. Alright, so getting back to here. Let's take a look at the representation of, let's say, 0.375. Okay, so we'll go ahead and reverse the process. So this time we say set var and dereference double star ampersand x equals to 0.375. Actually, better yet, let's make it 625, 0.625 right there. The brain budget, there's no such thing. It's a cash flow kind of thing. You use them, and then there's some income from somewhere else. I get my income to balance my cash flow from watching Elementary, the TV series. Alright, so we're going to look at this and then press the enter key. No problem, right? Okay, so before we get to, okay, I'm going to print x right now. Print x as a hexadecimal number. No, that doesn't look right. That doesn't look right. Oh, okay, I forgot to specify x here. Alright, so this is what x is. And now the question is, but Tech, are we really sure this makes sense? I mean, this is a chunk of bits of something, So what I'm going to do is I'm going to screenshot this. I'm also lazy when it comes to taking, recording something. So I'm going to take a screenshot just like you guys did. That's a really good technique, is to use screenshots. Okay, so I'm taking a screenshot and open it with FEH, which is my little program to display stuff. So now I have a little snapshot, and the browser can do whatever it wants now. And then we switch back to here, and then this time we are asking the question. Let me repeat the bit pattern here. So we have the hexadecimal number, which is 3FE4 and then a bunch of zeros. Okay, and we want to say, okay, not if I don't cheat, okay, and say, yeah, but I typed in 0.625 and that's why we got this. Assuming I did not, okay, assuming I was just given the base 16 representation here, and I'm supposed to find out what it is supposed to represent as a double. Now I need to reverse the whole process. So to reverse the process, I'm going to look at each hexadecimal number, 3F. Okay, let me space out a little more. So 3, 1, 2, 3, 4, F 1, 2, 3, 4, E 1, 2, 3, 4, 4, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on. That sounds like a music lesson. Except in music, you don't have to count using hexadecimal numbers. That would be a pretty interesting piece of music if you need to use hexadecimal number to count the beats in the bar. Alright, so 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, and the rest are all zeros. Okay. So now what we do is we break it apart. Okay, so we take this bit pattern here, and then I'm just going to copy and paste, so that if you guys want to find out, how I got that. So the first thing is I get rid of the spaces first, because the division by chunks of 4 is only for base conversion purposes. But when we want to actually interpret the bits, we don't want those spaces here. Instead, we want to put the spaces 1 over here to separate the sign bit, which is the most significant bit, from the biased exponent, which has 11 bits. So now we count 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so these 11 bits are the signed, excuse me, not signed, but the biased exponent. And then the rest over here would belong to the fractional part of the Mantissa. Alright, so now that we know this, we say the sign is a 0, which means the value is non-negative. Okay, very good. And then now we also know the biased exponent in base 2 is 0, and then 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a 0. This is in base 2. So right away we want to figure out what is the unbiased exponent in base 2. So what we need to do is to take whatever value the unsigned interpretation of this value is, and then we subtract 1023 from it. Okay, So you look at this and go like, wow, Tech, there are a lot of ones over here. What are we gonna do? I mean, this is gonna take forever to figure out. Well, there's another way to do this. So the other way to do this is to look at this as 1 followed by just a bunch of zeros in base 2 minus 1 0 in base 2. Because this quantity, if I put parentheses around the whole thing, is the same as the other quantity over here. And then we want to subtract 1023 from the whole thing. This 1023 is expressed in base 10 and hence no suffix, no 2 in parentheses. Alright, so that looks a lot easier because this is just 1024 minus 2, the whole thing minus 1023. And if you look at this, if you do your math, 1024 minus 1023 is 1. 1 minus 2 is negative 1. So we have a negative 1 over here. Yeah, okay. Okay, so we know the actual exponent of 2 now. Now we look at the fractional part of the Mantissa. So the fractional of Mantissa is 0, 1, and then just a whole bunch of zeros. So that means the Mantissa, which has an implied 1 point, and then we just append the rest to it. And those are all in base 2. And I'm going to take a look at the text channel because I heard that notification. I don't understand why he did the 1 0 in base 2. Oh, that's just a math trick that I did. Because I look at this number here, I am not going to add 9 powers of 2. So instead of looking at this number here, I'm going to say, I'm just going to say, it's the same thing as this whole thing, 1 followed by 9 zeros minus 1 0 in base 2. It's just that I know my binary subtraction really well, so I can look at this and immediately recognize that I can shortcut the whole thing. Instead of adding 9 powers of 2, I just have to say, okay, one is 1024, the other one is 2, do the subtraction. That's a whole lot faster compared to adding, these 9 powers of 2. Because otherwise, the other alternative, if you don't mind, adding powers of 2, you'll just be adding 2, 4, 6, 8 all the way up to and including 512, which should add up to 1022. So does that answer the question, Maddie? Okay. All right. So the trick is, okay, 1 followed by a bunch of zeros in base 2. Okay, I take it back. Sorry, a bunch of ones in base 2. Okay, it doesn't matter how many ones as long as they're contiguous. Is 1 followed by the same number of ones in base 2 minus 1. So that's basically the trick, the principle of the trick that I was using over here. Okay. All right. So getting back to here. All right. So now we have figured out all the parts. Okay. We have figured out all the parts. So the value. Oops. I shifted my key a little bit, and it typed out something funny. So the value that we are representing here is basically the same thing that we had earlier, which is the Mantissa times 2, because the whole thing is in base 2, to the power of the exponent of 2. Not the biased version, okay? This has to be the adjusted, the unbiased version. So in this case, the Mantissa is 1.01 in base 2 times 2 to the power of negative 1. And now we just have to do a very quick conversion from 1.01 in base 2 to the familiar version that we can see, that we can understand, which is base 10. So this is 1 plus no halves and then 1/4, right? So 1 plus 1/4. No, I must have done something wrong here. I'm just thinking, what did I miss? I think I did something wrong, but let me just work this out and see whether that works. No. Okay, I take it back. I didn't do anything wrong. Okay, so it's all good. It is all good because I forgot that I have to multiply the whole thing with 2 to the power of negative 1. Okay, there we go. And then we still have the multiplication of 2 to the power of -1, which is basically just 0.5, right? So now we have 1.25 times 0.5, and that turns out to be exactly 0.625. So we got our value back. No, I don't have to shift the point. I mean, I can shift the point, or I can just carry out the calculation like this. And then Matty said you used equivalence to maintain the value, but make it look more manageable. Okay. So the other approach, which is what Richard said, is to shift the point. So I can always shift the point so it becomes 0.101 in base 2 times 2 to the power of 0. So that's the other way to do it, is to shift the point on the Mantissa side and then get rid of the exponent, because 2 to the power of 0 is just 1. So in this case, it boils down to 0.5 plus 0.125, which is also 0.625. The 0.5 is coming from this one here, is contributing to the 0.5 because this one is representing that we have 1 of 2 to the power of -1. We don't have anything for 2 to the power of -2, and then we have 1 of the 2 to the power of -3, which is the 0.125. So when you add up the 0.5 and the 0.125, then we get 0.625. So that's the alternative way to get to 0.625. So there are a few ways to do it. Whichever way you want to use is fine. All right. So basically, you did 1022 plus 2 minus 2. Not really sure what you mean by plus 2 minus 2. The 1022 is 1024 minus 2, and then the whole thing has to and then we have to subtract 1023 from it. So the alternative way to do this is to say we have 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 225 plus 512, and then we subtract 1023, which should come up as -1 as well. All right, so basically he, instead of trying to add something like 999 plus 1024, he changed it to, something like that. Because this particular bit pattern is also just it's also this expression. And this expression is easier for me to deal with because I just have to figure out the difference between two powers of 2. But if I were to use the most standard way to do the base conversion, then I end up with the addition of 9 powers of 2, which add up to exactly 1022. It's just that it takes a little bit more time to do it. Is that good? I mean, are we getting that part cleared up? I mean, the other way to do this is to kind of copy and paste it into a calculator that can handle base 2. I mean, that's the other way to do it. I mean, many ways to do it. All right, so we are going to move on to talk about today's lab a little bit. So today's lab has a few things where in terms of math concepts, you probably want to keep in mind of those math concepts. It's really kind of the same thing. If you have 2 to the power of y equals z, then you can take the log of both sides. So you have log of x to the power of y, is the log of z, and the left hand side becomes y times the log of x, and the left hand side is still the log of z. So this is one really useful thing that you can do. And then the other one, let me see, are there any other rules that are really useful? Oh, right. So there's one question that will ask you, if you use if a single unit is a power of 2, and it's going to be given in your question, and then it's asking you how many of those units do you need to make up for a particular value, and to the closest, possible unit. That really is boiling down to the same thing as asking you if you need to make a change for $16.30, okay? But all you can use are quarters, okay? How many quarters do you use to come closest to $16.30? So it's basically just a rounded division to do that. So that's one. The most difficult question of today's lab is the one where you have certain constraints, and you have to find out, using the constraints, what representation is needed. So in that particular case, you basically say, okay, what if I just make it equal to one side of the constraint, figure out the irrational number as an answer, and then you say, what if I make it equal to the other end of the range and solve for the irrational number on the other side? So the correct answer would be the not rational number. The correct answer is going to be integer between the two rational numbers, which can only be one apart. So that's the way to solve one of those problems. In fact, I am going to explain that now. Okay, so don't go away, because I am going to explain to you the technique to answer one of the questions in today's lab. Alright, so let's go to today's lab, which is floating point 2. First of all, we want to... I'm just going to do a preview here. And then I'll show you the... let's see. Yeah, I think I'll just show you what question that I'm talking about, and the technique to solve that particular question. Let's see. Yeah, this one is just an algebra thing. And question. So there are 4 types of questions, and then the 4 types basically repeat themselves. One question needs you to understand what is rounding versus the floor. So I think it does explain, there are links here to the definition of floor. So the floor of a particular value is the largest integer that is less than or equal to the value. Rounding, already, okay, because rounding is 14.55 is rounded up to 15, 2.3 is rounded down to 2. So the rounding problem should not be as big of a should not be a big problem. Question number 3. This is the one where you need to find the number of units to make up a particular value. So it's really just a straight division. Okay. Remember the analogy that I gave you. Okay. You have $16.30 as a change, but all you can use are quarters. So the question is, how do you figure out the number of quarters to approximate 16.3? And it can go over, it can go under. I just need the one that is the closest. So, but I need to know the number of quarters in that case. So it's about the same thing, except we're not dealing with quarters in this particular case. We are dealing with 2 to the power of negative 21 instead of 2 to the power of negative 2. But the idea is the same. Okay. And then question 4, I think, is the hardest one. So this is the one where you have a range of values. So I need x to be between 2 to the power of 52 and 2 to the power of 53 minus 1. And the question is asking, I want to express, let's see, where's the value that I'm supposed to express? So the value that I want to express in this specific question is 3.042 E22. So remember, this E is not the natural log E. Okay, so I'm not gonna remind people anymore, because at this point I'm already nagging. So the question is, if I want to represent V in the form of x times 2 to the power of p, where p is an integer, what is x? Okay, that is what the question is asking. So there are many ways to find the answer of this question. The easiest one is to solve for x being exactly 2 to the power 52, figure out what that p is supposed to be. That is going to be an irrational number. Then you say, what if x is exactly 2 to the power 53? Solve for that x, which is also solve for that x, which is, excuse me, solve for that p, because we know x is here and then we know x is here. You solve for the two p's. Okay, each one is going to be an irrational number, but you will find that there's only one integer between the two irrational numbers. That integer between the two irrational numbers is the answer. Okay, so by the time you get to question 4 or question 8, they have the same format. All right. You also might want to jot down the time right now, which is 10:23, because in case you cannot remember all I just said, and you get to question number 4, you can always rewind today's lecture recording to this time and then watch this portion again. All right, so now that we have said all of that, let me give you the key to get started. And we have until, as usual, 1:20 to turn everything in. And this one also just keeps the highest score, so that makes it a little bit easier. You can see your feedback. Okay. The key to get started with this particular quiz is EXP. I put it into the text channel, and then I'm going to adjust the due date, which is 1:20. Okay, 1:20 p.m. 1:20 p.m. and save and publish. There we go. Alright, so you should be able to get started with this lab. You can use Mathematica, you can use your scientific calculator, you can just use a piece of paper, you can use a spreadsheet, use whatever tool that you are comfortable with, because there's a little bit of math involved, so you definitely want to use something that is capable of dealing with log and exponent. That would be helpful. I personally like the use of a spreadsheet, simply because once you figure out the formula to figure out the answer, you know that you're going to need it again, because the first 4 questions and the second half, the next 4 questions, they are the first and the 5th are the same kind of question. The second and the 6th are the same kind of question. So once you use a spreadsheet and figure out the formula, you just plug in different values and you get the answer right away. So there you go. Unless there are questions that I can answer that addresses the entire class, I'm going to get out of the voice channel. And Lisa is typing something, so I'm going to wait until she's done typing. All right. I am not seeing anything or activity in the text channel, so maybe that's not intended for me. All right, that's cool. I am going to get out of the live stream and also the screen share.